Today we talk about the Fundamental Theorem of Calculus, which, as the name implies, is a pretty important theorem in calculus. In fact, the Fundamental Theorem of Calculus is so important it has its own acronym, FTC, not to be confused with TLC. That was a hip-hop group from the 90s. T-Boz was the cutest member, by the way. But the Fundamental Theorem of Calculus gives the precise inverse relationship between the derivative and the integral. Newton and Leibniz, who are typically credited with the discovery of calculus, or at least they were the two who put all the pieces together, they used this relationship to develop calculus into a systematic mathematical method. They saw that the Fundamental Theorem of Calculus allowed them to compute areas and integrals very easily without having to compute them as limits of sums as we did in sections 5.1 and 5.2. So if you remember when we did this in section 5.2, there were a couple of them in the homework, and they were really easy. A first degree polynomial and a second degree polynomial. And they still, even though it was such an easy question, it took a ton of work to get the answer. So the Fundamental Theorem of Calculus allows us to skip all of this as long as we can find an antiderivative. And it's really hard to exaggerate how important this is. So we have this Stewart book, which has the #1 market share in the United States, but probably the second most popular is a Thomas and Finney text. Some of you transfer to Michigan State, I believe they use it over there, but it's written the same way. It's a very well written book, like Stewart, and even a lot of the sections are the same. But this is a quote they wrote in there. It says, "The independent discovery by Leibniz and Newton of this astonishing connection between integration and differentiation started the mathematical developments that fueled the scientific revolution for the next 200 years and constitutes what is still regarded as the most important computational discovery in the history of the world," which is a pretty bold statement, but realistically, if we didn't have this Fundamental Theorem of Calculus, we would be able to get to about the Industrial Revolution, and it would be hard to advance much beyond that without this. So although that sounds like a bold statement, most math and science historians would agree with that. And Stewart actually says something similar on page 399. Makes a pretty strong statement about how important this theorem is. So the world would be a lot different place if we didn't have this Fundamental Theorem of Calculus. And it's actually in two parts. So the first part, which will not be as important for us, but we'll talk about it. This first part, Fundamental Theorem of Calculus Part 1, states that the process of integration and differentiation are inverses. And this part of the theorem guarantees the existence of antiderivatives for continuous functions. Now, this is a little misleading. So, just because this exists doesn't mean it's going to be easy to find. In fact, it may not even be possible to find in terms of ordinary functions that we're used to using, so that you may actually have to make up a function in order for the antiderivative to exist. But in theory, it exists. So we will talk about the difficulties involved in finding antiderivatives a little bit in Calc 1, but mainly you'll spend time on that in Calc 2, where you'll learn a lot of approximation techniques. So the note here has to do with what we just mentioned, and we should be aware of this. The antiderivative may not be expressible in terms of elementary functions. And when you say elementary functions, it sounds like, oh, you mean easy ones? No, I mean basically anyone you've ever heard of, including things like inverse hyperbolic secant. That's an elementary function. So what is said a lot of times is there's no closed form solution. That's sometimes just said. It means the same thing, no closed form solution. So basically the difference between finding a derivative and finding an antiderivative is pretty stark, actually. It's difficult for me to come up with a function where you cannot find the derivative to that function. Our differentiation rules work really well, and you can pretty much always find a derivative. But going in the reverse direction, finding an antiderivative is often very difficult. And in real life, in applied problems, if you come up with a mathematical model, chances are pretty good that you won't be able to find an antiderivative. What that means is one in terms of elementary functions that we've heard of. And what'll be said is there's no closed form solution, which isn't that big of a deal because we'll use approximation techniques like Taylor series and others. So just kind of keep that in mind. And then so here is this Fundamental Theorem of Calculus Part 1. And this is the part that we're not going to use this part as often. It's not as useful for us in an applied setting. So I'll talk about it a little bit. It basically says that if f of x is continuous, which is pretty much how all of our theorems start off in calculus, we deal with continuous functions. So it's continuous on AB. Then this function g of x defined this way. So if you notice, g of x, this function is an integral. So g of x, which is the integral of f of t dt, and from a, which is a constant, to x, which is a variable. So the upper limit is a variable. Let's make a quick note of that here. Upper limit is a variable. And so if this function is continuous and differentiable, continuous on the closed interval, differentiable on the open interval, which just means the endpoints, it doesn't have to be differentiable at the endpoints, then the derivative of this, so you take the derivative of g of x and you get this function evaluated at the upper limit. So it's kind of like this. If you take the derivative of this, and the integral goes away. So it's basically saying that these are inverses of each other. Like when you take the square root of a square, the square root and the square cancel each other. It's the same sort of idea. So there's a picture here that is showing what this is saying. So g of x is this integral, but the upper limit is a variable. So it's the integral of f of t. So t is the independent variable. So here's f of t. So here's this function, and think of this x as sliding along here. Sometimes it's called the area so far function because since this is a variable, it can slide along here. So this is a picture of this integral, right? So when you have an upper limit that's a variable, then this upper limit can slide along here. So it's the area so far. So right now, this is the area underneath this curve from a to x, and x is right here. And then since it varies, maybe x could be over here next time, and then you'd add on this little piece of the area here. So we're not going to do much with this. I'll show you pretty much what we'll do, and then you won't really see it in your study of calculus, except for you math majors will run into it some more. But as far as going into Calc 2 and 3 differential equations, you're just not really going to see it. So a little note here is that the derivative of a definite integral with respect to its upper limit so the derivative of g of x with respect to x in this case is the integrand. Remember, the integrand is this thing right here. That's the integrand f of t. Is the integrand evaluated at the upper limit. So we can see it right here. If we take the derivative of g of x, which is a definite integral, so take the derivative of g of x with respect to its upper limit with respect to x, we're going to get the integrand evaluated at the upper limit. So you take the derivative of this thing and you just get f of x. So g prime of x is f of x. And there's an alternate notation here, which is probably a little bit easier to see. So I'm going to write this alternate notation here. And that just says this. If you take the derivative with respect to x of this integral, you get f of x. So here's what this says. If f is integrated and then the result is differentiated, we end up back at the original function. And we'll do a problem in the book that shows that this is true. But as far as the fundamental theorem of calculus is concerned, here's the kind of question we'll see in Calc 1. Basically, these are going to be, for us, really easy questions because we just have to know how to use this problem. In the details behind it, like I said, you typically study in an analysis class, which is sometimes called advanced calculus. So as a Calc 1 student, this is part of the theorem we're not going to use much as part 1. I'm kind of getting this out of the way, and then we'll do what we're going to do throughout calculus, and whenever you use calculus in other classes, we're going to pretty much always be using part 2. But here's what part 1 says. First, notice that this can be any constant at all. If I change this to 7, my answer is going to be the same. If I change it to 2/3, answer is the same. So this is saying I want to find the derivative of this function. So we want to find the derivative of this function, which is actually an integral. So it's using the fundamental theorem of calculus part 1, we just say, okay, g prime of x is equal to natural log of x. And that's it. We're done. Because we're finding the derivative of an integral. And according to the fundamental theorem of calculus part 1, the derivative of this with respect to x is this integrand evaluated at the upper limit. So for this to work, the upper limit has to be a variable. So if for instance we had a problem where, let's say, x is down here and 1 is up here, well, if you guys remember, we had that theorem that said that a to b f of x dx is the opposite of b to a f of x dx, right? So we saw this mentioned in a previous section. So if this had said x to 1, we would just switch them around and put a negative in front, and then we could use this theorem. Okay, so this isn't going to be a big part of what we do. It's just we have to be kind of aware of it, and we'll have questions, a couple, maybe 2 or 3 questions like this in this section of the homework, and then realistically, you won't really see this again until later. But or actually, many of you will never see it again. If you're a math major, you'll see it later. But the heart of everything that we're going to do is the second part of the theorem. And this is like, it's almost shocking. Like it's really surprising that this could even work, which is probably why it took so long for people to figure out. Although Isaac Newton's his teacher knew there was some sort of connection, but he couldn't quite show it or prove it. And then Newton and Leibniz independently ended up, they kind of saw all the pieces. There were people working on individual pieces, but they were the ones who had enough insight to put the pieces together. So the second part of the theorem, Fundamental Theorem of Calculus, Part 2, states that the definite integral of a function can be computed without taking limits, without calculating Riemann sums. I know you guys are going to miss those kind of problems. And often with little effort, as long as an antiderivative can be found. If you can imagine what it was like before this theorem and before computing machines, when approximations by tedious sums were the only alternative for solving many real-world problems, then you can imagine what a miracle calculus was thought to be. So here is the Fundamental Theorem of Calculus, Part 2. And I saw a quote, and it said, this was from Isaac Newton. I know it's true because it was in all caps on the internet. And Isaac Newton apparently said that the Fundamental Theorem of Calculus, Part 2, is sometimes called the Chuck Norris theorem because it kicks ass. That's what I heard. I know it must be true. But here it is. The Fundamental Theorem of Calculus, Part 2 says, if f of x is continuous on AB, then integrating this, so we're going to integrate this function from a to b, and it turns out we can turn it into a subtraction problem as long as we know an antiderivative. In other words, this is like 4.9 notation, right? Capital F is the antiderivative of little f, so f of x is any antiderivative of f of x. In other words, big F prime equals f. So there's a way we denote this too, and this is important too. We have to know how to denote this, right? So we have to be able to, we don't want to look like a newbie, right? Denoted f of x from b to a. So this is where, you've seen this before, this is a straight line. So normally we integrate this, we'll put it like this, we say this thing equals this. And then the next step is we plug in a b, and we go minus and plug in an a. That's where this is coming from. So here's what this theorem means. Let's say we've got this function, and it's just weird. It's just a weird looking function like this. And let's say we want to know the area underneath this curve. I'm going to interpret this as an area problem just so it's easier to talk about. So we've got this weird function, y equals f of x, and we're trying to figure out this integral, right? Which in this case can be interpreted as the area under that curve, and we're like, oh my God, I have no idea how to find this area, or how to integrate this. And here's what somebody's going to tell you. You say, oh, it's easy. All you need to do is figure out the antiderivative, and then plug in the two endpoints. Plug in b, and then subtract a. That's all you have to do. And you're like, what do you mean? What about all this in the middle? Don't worry about that in the middle. Just find the endpoint at b, find the other one at a, and subtract them. You're like, that's all? I don't have to pay attention to any of this stuff? Any of this weird stuff here? No. Just find f of b and f of a and subtract them. That's your answer. That's what the Fundamental Theorem of Calculus says. And if that seems a little surprising that it would work like that, well, yes, that was surprising to everyone, which is, like I said, probably why it took so long to put all these pieces together. So, remember when we're talking about these definite integrals, I keep talking about in terms of an area. Just like with derivatives, we talked about derivatives in terms of slopes of lines. But really, these areas in applications can be interpreted as volumes, lengths of curve, velocity, power, energy, acceleration, all kinds of things. Basically, wherever you can relate two variables to each other. So I'm teaching this in terms of areas because it's kind of easy to get a picture of that. But when we get into the problems, we're not really going to be finding areas. We're going to be integrating for other reasons. So the note here, just summarizing this surprising theorem, it can be summarized like this. We can just say we can evaluate this integral of f of x dx from a to b simply by subtracting the values of f, and f is just an antiderivative, right? We need to be able to find the antiderivative at the endpoints of the interval. So, as we'll see, there are a lot of functions with known antiderivatives. And if you have a function with a known antiderivative, it's super easy to differentiate. Just turn it into a subtraction problem. So a lot of times you'll have a function where it's not in a perfect form where you can look in a table, like in the old days there were tables of integrals in the back of a calculus book. You look in the table and say, okay, I've got this function here, here's the antiderivative. So we'll learn some techniques. We'll learn what's called U substitution, where we'll take a function and transform it into one that we know, and so that we can have the antiderivative. And then, as I kind of hinted to, you see that in reality, finding this antiderivative is sometimes just impossible or extremely difficult. And in that case, we won't actually use the fundamental theorem. We'll use an approximation technique. But at first, we're going to use this theorem all the time because we're going to see functions where we can find the antiderivative, and then we're just going to plug in the endpoints. So this first example, I'm picking this example because this problem right here seems kind of simple. Find the area under the cosine curve. This was first found in 1635. This was like a big thing. 1635 was first found. This is before the Fundamental Theorem of Calculus. So to find it, limits, you had to use the limits of Riemann sums, and there were a lot of obscure trig identities required, and you really had to be an extremely skilled mathematician to figure this out. And now we're going to be able to figure this out in probably 2 minutes or less because we have the Fundamental Theorem of Calculus. So basically, here's the question. 0 to pi over 2 cosine of x dx. This question right here, without the Fundamental Theorem of Calculus, required pretty much a top-rate mathematician, or a bunch of them, to come up with a lot of obscure trig identities and go through the technique we used in 5.2, the limit of Riemann sums, and it was a very challenging problem. But with this new theorem, it's a very easy problem because all we have to do is think of this. What's the antiderivative of cosine? You guys all know it, right? The antiderivative of cosine is sine. I'm going to mention some things that have to do with the notation. So we put the antiderivative here, and now that long s turns into a straight line. So this like elongated s that we use for integration turns into a straight line. Remember, when this integration, this long s is gone, what else is gone? Dx. Remember, I mentioned that these two go together. They're either both there or neither is there. So once we integrate, this is gone. And this takes a little practice because I'll see students all the time who will do things like this. They'll say, okay, cosine of x dx equals sine of x. And it's like, you don't want to do that. It's sort of like when my students in remedial algebra will do, okay, the square root of 16, that's 4, and then they put the square root there again. And then they say it's 2, right? It's just like, it's kind of a mistake you can make when you're new. So you don't want to do that. This is pretty much the same mistake. Once we integrate, when we find the antiderivative, this is gone. When that's gone, dx is gone. Okay, they have to both go together. So let me get this out of here. I know some of you don't even like to look at that. I know, I don't either. Okay, so the notation we use is now we have these upper limits like this. All right, so this is Leibniz notation. It's pretty much standard though. We take this question is saying what is the integral of cosine of x dx from 0 to pi over 2? Here's our answer. It's sine of x from pi halves to 0. And now from the Fundamental Theorem of Calculus, we plug in this one first, always the top one first, and then we subtract and we plug in the bottom one. So the answer is sine of pi over 2 minus sine of 0. Right, so this is pretty much the notation we want to use on these problems. We go from here to here, and we plug this in to get here. Now sine of pi over 2, if you remember the sine function, pi and 2 pi, remember sine goes like this. So pi over 2 is right there, so sine of pi over 2 is 1. So the answer is 1 minus 0, sine of 0 is 0, so we get 1. That would have taken a whole lot of time and a whole lot of skills and knowledge of math and trigonometry to figure that problem out without the Fundamental Theorem of Calculus. So I'm going to write some problems down, and this is where normally in class would have you guys work on these. So try them out. Don't wait for me. Try them out first. Press pause, right? And then check back. So I'm just going to, go through and explain them, but make sure that you, when you're watching this, press pause and try them yourself. So here is a problem. 1, x to the 10. X to the 10 would be good, but it would be better x to the 100. Oh my gosh. You wouldn't want to do this one the old way. That would be a lot of work. But this one is kind of easy for us because this is just a power rule, right? We can definitely find the antiderivative of this function using the power rule. This goes up by 1. We divide by that. So this is going to be x to the 101 divided by 101. And then we have 1 to negative 1. So remember, we want to get used to this notation. When the integral is gone, the dx is gone, right? There's no dx here. Integral and dx go together. That's like one symbol. And then from here, we plug in 1 in for x. Then we go minus. Then we plug in negative 1 in for x. So we get 1 to the 101 over 101 minus, it's automatically a minus, right? F of b minus f of a, minus 1 to the 101 over 101. So this is 1 over 101 minus, well, this is negative raised to an odd power. So the answer to this is going to be negative 1. So you have negative 1 over 101. And then we have minus minus, which I know what you guys do when you see minus minus. Make this giant plus, right? 1 over 101 plus 1 over 101 equals 2 over 101. And remember, with these definite integrals, you can check these on the calculator. Remember, we talked about that in the last section. You use the finite integral command. And this will work on the TI-83 or 84 as long as it's a definite integral, which these are. Definite integral means you have your lower and upper limits. So make sure you're comfortable with this command too. It's nice just to be able to to find it in integral and to check your answer. And just in case you don't remember, press this finite integral command, you press the math button and go down to number 9. And if you have the math print, it's really self-explanatory. If you don't, if you have the older version, you just have to type x raised to the 100 comma x. Remember, this is the variable we're going to integrate with respect to. I'm not really sure why it makes us do this, because there's only one choice. It only does single variable calculus. So anyway, plug that in there, -1 to 1. And you should get a decimal, but then if you hit math enter, it will convert it to a fraction. And then you should get the same thing that we got here. Okay, we've got another problem here. And when you look at this one, we don't really, have an antiderivative of this the way it's written. So what we'll probably have to do is algebraically tweak this, which we can do easily enough if we distribute this through. And just remember that the square root of t is just t to the 1/2 power. So think of distributing the t to the 1/2 power through, and then we just use our rules of exponents. So that would give us 4t to the 1/2 minus t to the 3/2 dt. Right, because t to the 1/2 times 4 is easy. T to the 1/2 times t to the 1, you add them, right? So that's like t to the 1/2 times t to the 2/2. So you get t to the 3/2. So then from here we're ready to go, because we can use the power rule for both of these. So that's going to give us, so right here, t to the 1/2, we go up by 1, right? 1/2 plus 2/2 is 3/2. Then we divide by 3/2, but what's easier than dividing by 3/2? Multiplying by 2/3. Right, so I have 4 times 2/3 t to the 3/2, right, which is just the power rule here. Remember, because I add 1, so 1/2 becomes 3/2, divide by 3/2, but that's the same as multiplying by 2/3. And then I have this one. So same sort of thing, 3/2 plus 1 is 3/2 plus 2/2, which is 5/2. I have to divide by 5/2, but instead of that, I'm going to multiply by 2/5. So we get minus 2/5 t to the 5/2 from 4 to 0. And you can look at the notation here. This says integrate this function, right? You have the integration symbol and the dt. They always go together. Once we integrate, we're here. That goes away and that goes away. There's no dt. There's no squiggly s. We integrated, so here's our antiderivative. Here's a straight line evaluated here. So the Fundamental Theorem of Calculus says the answer to this is the antiderivative evaluated here minus the antiderivative evaluated here. Now you can see when you plug in the 0 for t, we're just going to get a 0. But before we plug in the 4, let me move this up and make it, just clean it up a little bit. So this is really 8/3 t to the 3/2 minus 2/5 t to the 5/2 from 4 to 0. And I know you guys are going to want exact values, so you're not going to want to reach for the calculator yet, because we can do this. We can go 8/3 times 4 to the 3/2 minus 2/5 times 4 to the 5/2 minus, and when I plug in the 0, I'm just going to get a 0, right? So I'm putting this just so we don't forget. This is f of b minus, here's f of a. When I plug a 0 in here, I get 0 minus 0, which is just 0. So we mainly just have to worry about this. So 4 to the 3/2, 4 to the 3/2, there's two ways you can think about this. You could think, well, that's really 4 to the 1/2 cubed, right? Rules of exponents, we multiply here, we get 3/2. We know this answer. What's 4 to the 1/2? That's just the square root of 4, right? That's just 2 cubed. And that's going to be 8. So 4 to the 3/2 is 8. The other way you could do it is like this. Here's what some people do. They like to make it an integer power and then write whatever is left. So again, just a different way, just a different approach. 4 to the 3/2. This, when we use this rule of exponents, we add these 2/2 plus 1/2 is 3/2. And this is just 4 to the 2/2, it's just 4. 4 to the 1/2 is the square root of 4, which is 2. So either way, we get 8. So this is going to be 8/3 times 8. Okay, and then we have something similar here. We have 4 to the 5/2. So again, I'll do it both ways. You guys can pick whichever way you like, but of course you could use the calculator, but if you want to get the exact value, it would have worked on the last one. But in this case, it'll work on this case too. So I guess we're just practicing now. There's just a little practice. So this would give us 2 to the 5th power, which is 32. The other way you could think of this is this. You could think, okay, I want to have 4 to an integer power. The highest integer power I can get here is 4/2, right? And that'll leave me with 4 to the 1/2. And 4 to the 4/2, that's 4 squared, which is 16, times the square root of 4, which is 2, which still gives us 32. So this gives us minus 2/5 times 32. So what I'm looking for on the test is to show me that you know calculus. So from this point, I need you to show me you know how to put the 4 in and then the 0, because some students will reverse these. So once you get right here, okay, once you have done this step, beyond that is arithmetic. I know everybody can do arithmetic. So from here, you could actually just use finite integral and write your final answer there. Okay, you don't need to convince me that you know how to do arithmetic, but I do need to see this. I need you to show me that you understand that once you take the antiderivative, the 4 goes in first, then the 0. So I need to see this step, and after this, all I need is the answer. So you can do this if you want to, but you don't have to. So, in other words, just for practice, I'm going to do it in here. Right, so just again for practice, subtracting fractions is a really easy way to do that. Adding and subtracting fractions, I never go through common denominator and all that kind of nonsense. I mean, I do, but in a quick and easy way. So what I do to do this problem is this. I do it in one step. Do you guys agree that when I multiply these two together, I will get a common denominator, even if it's not the least common? Right, so 3 times 5 is 15. I put that here. And then I multiply crossways. 5 times 6, 40. Here's the easy way. Don't multiply by 5, multiply by 10 and then take half, which is the same as 5. So 10 times 6, 64 is 640. Take half of that is 320. So I'm going to put 320 here. And then I go this way, 3 times 64. Well, 3 times 60 is 180. 3 times 4 is 12, so it's 192. And then I do whatever this says, minus. So I go minus 192. And then we just do the problem from there. So 320 minus 192 is 128 over 15. So that's the answer. But all of this here is optional. You don't have to show me that. I know that everybody's capable of arithmetic. So what the work I'll need to see is this step here. Don't stop here. Don't stop here. Because I'm telling you, from doing this many years, students are going to reverse these. So I can't assume that you know what to do from here. So show me that you know 4 goes first and then the 0. Then from there, you can do all this on your calculator, or you can use finite integral for the original problem and just write down the answer. Oh, did you guys see something weird about my answer? Oh my gosh, 15. Okay, I think that would be a better answer. Okay, so I know by now everybody's thinking, Kurt, how about a little trigonometry? It's like I can read your mind even through the internet. All right, let's try one. To save me from getting all the hate email about ignoring trigonometry. 0 to pi over 4, secant theta, tangent theta, d theta. So remember, press pause, try it on your own, and then check back. That's the best way to learn math, right? You guys know that. The best way is not by watching someone. It's by trying it yourself, hitting the little bumps in the road, and then learning from those bumps. So try it yourself, and then come on back. So for this one, we know the antiderivative of secant tangent. That's secant, right? Because the derivative of secant is secant tangent. And that line does not look very straight. Let me try that again. So the antiderivative of secant tangent is secant because, remember, the antiderivatives you can always check. Take the derivative of this and make sure you get back here, which we do. Now look, we have d theta this time because our independent variable is theta, so that will go along with this. But once again, once we take the antiderivative, the integration symbol and the d theta both go away, and we're here. And now the fundamental theorem of calculus says you can evaluate this antiderivative here minus this antiderivative evaluated here. So that gives us secant of pi over 4 minus secant of 0. And as we talked about many times, everybody learns SOHCAHTOA because that's all you need. You don't need to also memorize things for cosecant, secant, and cotangent. Just whenever you see secant, just realize, I'm just going to find the cosine instead and flip it over. So we've got pi over 4. So let's just review these two special triangles one more time. And I realize that some of you guys use a unit circle, so if you're using the unit circle, that works just fine too. But as I've just found it's easier to, because we don't cover this, it's easier to review it with the unit circle, or with the special triangles. So of course this is a 30, 60, 90, and this is a 45, 45, 90. We don't care about the 90, right? These are going to be used to find the acute angles, the 45s and the 30s and 60s. So 30 degrees is really the same as pi over 6. 60 degrees is the same as pi over 3. 45 is pi over 4 and pi over 4. And we are dealing with secant pi over 4. So in each case, the shortest side is always 1. The shortest side is always across from the smallest angle. So in this case, we could use Pythagorean theorem to get square root of 2 here. Now in this other case, just remember it's kind of easy to put these in. Just think 1, 2, 3. 1, 2, 3. So I have 1, 2, 3, and in this case the radical goes over the 3. So these are the two special triangles. So secant of pi over 4, I'm going to find cosine of pi over 4 instead. Cosine of pi over 4, here's cosine, adjacent over hypotenuse. Cosine of pi over 4 is 1 over square root of 2. So secant pi over 2, or secant pi over 4 is square root of 2 over 1, which is just square root of 2. Now secant of 0, well, for any kind of questions of trig functions that have to do with multiples of, well, 0, I guess, but multiples of pi halves or pi, I just go to the graph. Oh gosh, very bad at drawing, but this is a graph of the cosine function. So because I'm not going to look at the graph of the secant function because we don't need to, we can do the cosine and take the reciprocal. Cosine of 0 is 1. Reciprocal of 1 is also 1. So the answer to this question is the square root of 2 minus 1. And again, we're typically going to want the exact value. So we don't want to, for these trig functions, we don't want to just plug in the calculator and get a decimal approximation. In this case, because pi over 4 and 0 are special, they're called special angles because we can evaluate them exactly with the trig functions. We want this one to be exact value. And it'll tell you. Some of the questions I'll say give exact value. So remember, exact value is this. This is exact. Any decimal approximation, even if you approximate the square root of 2 to the millionth decimal point, or decimal place, it's still an approximation. This is exact, right? This is exact. So for a lot of these, I'll say give exact value. This is exact value. Okay, so then we've got a couple more we should look at, and then I think you guys will be good to go. So this problem, page 400, number 56, says, what is wrong with the equation? So we look at this, you've got this antiderivative of this function between -1 and 2, and then they do the work here. And this is the, if you integrate this, you'll get this, because, just to see what we've got here, this is really 4x to the minus 3, right? So we would go up by 1 to be -2, so we divide by -2. So if we were to integrate this, let me just do this real quick. So we have the 4x to the -2 divided by -2, right? And we've got, from 2 to -1, 1 to 2. All right, so then we would plug in, well, this would cancel. That's just 2. That's like a -1. So we have 2x to the -2 over -1. And then this, we can make a positive if we bring down here, and this is just division by -1. So we end up with -2x, or sorry, -2 over x squared. So just wanted to show you that's right. So they're not asking about something weird happening here. And then if you plug in the 2 and then minus and plug in the -1, you do get 3 halves. So what's the problem? Because this is the wrong answer. This is all wrong. You can ask your calculator to do this problem, which you should plug this in your calculator. Math 9, plug this in your calculator, and if it has computer algebra software, it's going to know what's happening. But if it doesn't, it's going to get confused. And it will typically spend quite a bit of time on this problem, and eventually will say something weird. Say some sort of error or tolerance not met. I'm running it on my calculator right now, and it's very confused. It's thinking. It doesn't really, my calculator is a TI-84. It doesn't have computer algebra software, so it doesn't really, know anything. It's just blindly running through the quartic algorithm, and it's just going to get to a weird point. It's going to kick out some sort of error. It's still thinking. I think it might be smoking a little bit. Oh boy, this is not good for the calculator. It's very confused. Okay, here we go. It says error tolerance not met. So the calculator doesn't know what's wrong, but it can see that something's not wrong. It's not getting an answer. So some of you, I'm sure, have seen it by now, but remember the fundamental theorem of calculus? When you read the part 2, which is what we're using, the first statement it says is if f of x is continuous on AB. Think if you were going to graph this between -1 and 2. Can you imagine any number between -1 and 2 that would give us issues here? 0, right? So the fundamental theorem of calculus doesn't work here because this function is not continuous from -1 to 2. This is called the improper integral, and in Calc 2 you'll learn how to evaluate this using, believe it or not, limits. But for us, we won't have one like this. We just, at this point, with what we've got so far, this fails the initial part of the fundamental theorem of calculus. This is not continuous here. So that's what they're getting at. So there's a couple of them like that. 55 to 58, they're going to ask you what's wrong with the equation. So that's the kind of thing that they're looking for. And then one more we should try is number 6. So this will show us a little bit about where both of those fundamental theorems come into play here. So number 6 gives us g of x, and it is the integral from 0 to x of 2 plus sine of t dt. And for number 6, we are going to find g prime of x in 2 ways. First, we're going to use part 1 of the fundamental theorem of calculus, and then we're going to evaluate the integral using part 2 and then differentiating. So they want us to find g prime of x. Find g prime of x. Okay, we're going to do it 2 ways. So first, we're going to do it with the fundamental theorem of calculus part 1. Okay, this is the fundamental theorem of calculus that you don't really use too much, but it's got kind of an answer. It always seems like kind of a strange answer, but that says to take the derivative of this. We're going to take the derivative of this function that's defined as an integral, and it basically says the derivative will cancel the integral, so you just get the integrand evaluated at the upper limit. So according to this theorem, we're going to get 2 plus the sine of x, and we're done. But that theorem's kind of unsatisfying because we don't have any intuition for it. It just says that's how it works. But here's how we can verify it. Here's what we're going to do, which is better than just blindly plugging this in. We're going to use part 2 of the theorem, which just says integrate this, and then plug in these endpoints, and then take the derivative. Okay, so this part is going to be, I think, more revealing and more satisfying to just like make sense of it. So let me shrink this a little. So for this part, we'll go with Fundamental Theorem of Calculus Part 2, and then we'll differentiate. So g of x equals 2 plus sine of t dt. So let's just integrate this. So the antiderivative of 2 is 2t, right, because t is our independent variable. And then the antiderivative of sine is minus cosine of t, and we go from x to 0. Right, so we're just integrating this. We're taking the antiderivative. Remember, integration is the process of finding the antiderivative. So find the antiderivative of this, which is here, right? Because if you differentiate here, you get back here. Because remember, the derivative of cosine is negative sine. So we need the minus here to make it a positive. Now we're going to plug in the limits of integration. So we're going to get 2x minus cosine of x minus, now I plug in a 0. 2 times 0 is 0. Cosine of 0 is 1. Right, so this is equal to 2x minus cosine of x plus 1. So that's g of x, right? That's g of x. Now they want us to find g prime of x. So from here we just take the derivative. So we know what g of x is. So then g prime of x, I just take the derivative of this. Take the derivative of this, you get 2. Then the derivative of negative cosine is going to be positive sine, right? So you get positive sine of x, and the derivative of 1 is 0. So we got this, and really this second part probably makes more sense, but we got this. But the first part got us the same answer. So I think you guys have one like that in the book number 5, very similar. It's just saying, okay, if we've got this function defined as an integral, here's why part 1 works. The derivative is the inverse of the integral, so they're just going to cancel out. And to show that that works, part 2 we can use to show that we will actually just take the integral and then take the derivative of our answer. So we get the same thing. So 5.3 is going to be important for us. 5.1 and 5.2, for most of you, it won't be a big part of what you do with calculus. If you're a math major or minor, it will be. But for most of us going into applied fields, 5.3 is going to be more important, and especially 5.4 and 5.5. So for those of you going into Calc 2, the end of Chapter 5 is going to be really important. So make sure you put in some time into the integral problems. And let me know if you have any questions.